Welcome to part 2 of our lesson on determinants and inverses. And as promised, I'm going to show you the use of the inverse and why are we learning this thing? What is it used for? So to do that, let's start with something a little simpler. Let's just start with a number. Suppose I give you a number. I give you the number 5. And I ask you, what number would you multiply times 5 to give me 1? If you thought about it for a minute, hopefully you would come up with the number 1/5. Because if I multiply 5 times 1/5, 5 over 1 times 1 over 5, multiplying straight across gives you 5 over 5. That's 1. And this works with any fraction like that. So if I have 6 times 1/6, also gives me 1. 2 times 1/2, 1. You can do it the other way around. You can say 1/3 times 3. That's also going to give me 1. So in any one of these cases, in all of these cases, when you multiply these two numbers together, you get a 1. This concept has a name. That means that these two numbers that I'm multiplying together are called inverses of each other. And that should look familiar because that's the name of the video and that's what we've been doing, right? So these two numbers are inverses of each other. What that means is 5 is the inverse of 1/5. And 1/5 is the inverse of 5. And why is that? Well, if you take those two numbers together, they give you 1. You can think of that as a relationship. They come in a pair. Okay, so if I said, what is the inverse of 6? You would say 1/6. And if I asked you, why is 1/6 the inverse of 6? You would say, well, because when you multiply them, you get 1. And if I asked you, what is the inverse of 1/4? You're going to tell me 4. And then I would ask, well, why is 4 the inverse of 1/4? They're going to tell me because when you multiply them, you get 1. So it's a relationship between two numbers that tells me that multiplying them together gives me 1. Okay? Well, this relationship exists in matrices too. So let me just show that to you. So if I had a matrix here, I'm going to call it A. Now, I could fill this with numbers, but that's not the point right now. I'm just trying to give you the concept. Okay, if I had a matrix and it had numbers in it, but I'm going to call it A, and I multiply it by its inverse that we learned how to calculate in the last video, what's it going to give me? Well, it's going to give me the matrix equivalent of 1. Okay, so let me say that again. So just like 9 times 1/9 gives me 1, because these are inverses of each other, well, A and A inverse are inverses of each other. So just like 9 times 1/9 gives me 1, A times A inverse is going to give me, quote unquote, 1. But that's the 1 in matrix terms. Okay? All right, so what does that mean? Well, I need to know what 1 looks like as a matrix. Let's do that first before we get into actually calculating these things. So if I'm working with 2 by 2 matrices, the 1 over here is going to look like this. Now, what do I mean by the 1? The 1 of matrices. Well, the other name for this is called identity. This is called the identity matrix. Identity, that's not how you spell that. And what that means is if I multiply this by a matrix, I get the same matrix back. Let me explain. So if I take the number 7 and I multiply it times 1, what do I get? 7. If I multiply 8 times 1, what do I get? 8. So multiplying 1 by a number doesn't change it. That's what makes it 1. That's what it does. This is the identity number. All right? Because it produces the same number every time. I could take any number in existence, anything at all. X, pi, I could multiply anything. 2.7 times 1 is what? 2.7. That's what makes it 1. So my claim is that this thing up here, this thing If I multiply it by a matrix, I'm going to get that matrix back. In other words, it doesn't change it. So let me prove that to you really quick. Let's try that. Let's go to a fresh page. I'm just going to take any matrix, it doesn't matter what, 3, 2, 4, and 5. I'm going to multiply it by the identity matrix. My claim is that it works just like 1. In other words, A times this identity matrix, we're going to use an I, is going to give me A back. It's not going to change anything. That's my claim. Let's try it. Okay, and we've done a lot of multiplication of matrices, but I am going to go through this and show you how I'm doing it so that you can be convinced that when I multiply these two things, it doesn't change the original matrix. So over here, I have first row times first column. 3 times 1 is 3, plus, well, look at this. That's 2 times 0, which is going to give me 0. So I'm not really adding anything to that. So it's just 3 times 3, or 3 times 1, plus 0, which is 3. All right. Now let's look at the top right one. That's row 1, column 2. That's 3 times 0 is 0, and then 2 times 1 is 2. So far, so good. Now, row 2, column 1, that's 4 times 1 plus 5 times 0. Well, 5 times 0 is 0, so it's just 4 times 1, which is 4. And finally, 4 times 0 is 0, plus 5 times 1 is 5. 0 plus 5 is 5. And look at that. It, in fact, didn't change the matrix. How cool is that? So I started with the matrix here. I multiplied it times this thing, and I got the matrix right back. So, in fact, this thing didn't change anything. So just like 8 times 1 equals 8, A times I gives me A. It doesn't change the matrix. All right? So my claim that this is the identity matrix is now verified, at least in this way. So now what we need to do is verify that if you do this kind of mess, this business, A times A inverse, it's going to give me that identity. So let's try that. So I'm going to give you a matrix A. And let's make it 5, 2, 3, and let's do 2 also. All right, this is my matrix. And we're going to find the inverse of this matrix. And then we're going to multiply it to see if, I'm going to kind of jump ahead here, when I multiply it times A inverse, is it going to give me this identity? That's what I want to know. All right, so let's try it. First, we got to find A inverse. And we practiced that quite a bit in the last video. That's what we did. And I wanted you to get comfortable with that first so that we don't get bogged down in all the details of the mechanics when we're trying to understand, why we're doing this. All right, so let's find the inverse. First of all, the determinant of A is going to be 5 times 2 is 10, minus 3 times 2 is 6, so the determinant is 4. All right, so now A inverse is going to be, remember I swapped 5 and 2 here, so that's just 2 and 5. I swap the sign of this one, I swap the sign of this one, just like that. And and I got to give myself some room here. Oh, the page is running away from me. A inverse equals, this is 1 over 4, right? So that was the first part. And now I have to multiply through with that 1/4. So let's do that. This is 2 over 4. This is negative 2 over 4. This is negative 3 over 4. And this is 5 over 4. And I'm going to reduce that. So to reduce that, I get, well, 2 over 4 is just 1/2. Negative 2/4 is negative 1/2. And then this can't be reduced anymore. And this can't be reduced anymore. So this is my inverse. So I did that kind of fast because I'm trusting that you know how to do the matrices, the inverse of matrices from the last video. You've got some practice with that. So what am I trying to do? Okay, my claim was, again, that if I multiply A times A inverse, I better get I, which is the identity matrix, the 1 and 0 matrix. And why am I doing that? Because I want to verify that just like 8 times 1 equals 8, not that. 8 times 1, 8 equals 1. It works the same way, right? Okay, let's do that. Here we go. We're going to multiply. Let's change colors because it's going to get crazy here. So here's A. I'm just going to write it down again. 5, 2, 3, and 2. And then here I'm going to write 1/2, -1/2, -3/4, 5/4, and now I'm going to multiply. And hopefully, if I did everything right, I should get the identity matrix, because this and this are inverses of each other. Okay, here we go. Let's do it. Let me just use a different color here. Okay, so I have row 1, column 1. That's 5 times 1/2, which is, I'm going to do some scratch work down here. That's 5/2, and that's plus, this is 2 times -3/4, which is -6/4. Okay. And that's going to be 5/2 minus 3/2, which is 2/2, which, look at this, is 1. So far, so good. I get excited when this kind of stuff works. I know it's supposed to work, and I know how to do it. I've done this for a while. I've done a million of these, but it never ceases to amaze me when it actually happens. I don't know why. Okay, so let's do row 1, column 2. This one and this one. All right, so this is -5/2 plus 10/4. Well, that is -5/2 plus 5/2. That's a -5/2 plus 5/2. Those are opposites of each other, so they just cancel out. What does that give me? 0. It's happening. Look at that. I'm getting excited. All right, let's do the next one. So now we have row 2 and row 1. Column 1, rather. So this is 3 times 1/2, which is 3/2. And then I have plus, this is going to be -3/4. In other words, minus, that's not 3/4, that's 6/4. I need to pay more attention to what I'm doing. All right, so now let's reduce that. I have 3/2. This is minus, if you cut those in half, you get 3/2. Well, that's just going to be 0 again. So there's my 0. We're almost there. One more. Oh, I didn't want to erase. Last one. Row 2 times column 2. So that's going to be -3/2 plus, that's 2 times 5 is 10/4. That's going to be -3/2. Now, if I divide both of those by 2, I get 5/2, right? Now, this is like saying 5 minus 3. -3 plus 5, same thing. That is 2/2, and boom. It gives me 1. Look at that. It works. So that means that when we did all this stuff up here at the top, where we created that inverse matrix, we were successful. I did all of that stuff just to prove that this is, in fact, the inverse. So when we made this matrix here, we did it correctly. Why did we do it correctly? How do we know that it was correct? Well, we multiplied it by A and got this identity matrix back. That's how we know that what we did was correct. Now, why? Why do I want to do all this stuff? We created it. We talked about what this identity matrix is, and we verified that all this stuff works. But it's not just for fun. I find it fun. I don't know if you do or not, but I do. I'm weird like that. But why are we doing this? Well, this is why we're doing that. Here's where it comes together. Let's say I wanted to divide some numbers. Let's say I wanted to divide 12 by 4. Well, one way I could do that is, well, divide it by 4, but another way you can divide by 4 is to multiply by 1/4, right? The act of multiplying by 1/4 is the same as dividing by 4. Now, it gives you 3, but that's not the point. What I want you to see is if you multiply by the inverse of 4, that's the same as dividing by 4. Let me actually write that down in English. So dividing by 4 is the same as multiplying by its inverse, which is, of course, 1/4. So having inverses gives us a way to divide things. That's what they're used for. Now, if you multiply something times its own inverse, you get 1. But if you multiply something times something else, an inverse by something else, it actually performs division. Let me show you another one. So if I had, 15, and I want to divide it by 5, the alternative method of dividing this by 5 is multiplying it by 1/5. In other words, multiplying it by the inverse of 5, because this is the inverse of 5. Okay? Hope this is making sense. I hope you see where this is going. Let's try another one. If I wanted to do, like, say, 20 divided by 4. Okay? I used 4 again or earlier, but that's okay. So if I wanted to do 20 divided by 4 and I wasn't allowed to divide, that's okay, because I know another way to do it. I can just go 20 times 4's inverse, and that performs the same operation. It does the same thing as division, which gives me 5. So why is this important? Well, if you think about it, we know how to add and subtract matrices, and we know how to multiply them, which is great, but we don't have a way to divide matrices. Well, now we do. Because if you want to divide a matrix, all I have to do is multiply by an inverse. So let me give you an example. And I'm not actually going to calculate all of this because the calculations themselves get really hairy, really messy and nasty. But I just want to show you, at least symbolically, what I'm trying to get across here. Let's say I wanted to divide. I know this isn't actually a thing you can do, but that's my point. If you wanted to divide, quote unquote, A by B, that's not a thing we can do. We don't have a way to divide matrices, but we can multiply them, right? So if I were to find the inverse of B and multiply it, this becomes the same thing. So I've accomplished essentially the act of division by finding inverse. And that's going to give me the answer of whatever would be A divided by B. Okay? So I'm not actually going to do one, like I said, because finding an inverse and multiplying it times itself or times its inverse turns out to be nice and pretty. It's ones and zeros. When I actually do this calculation, it gets pretty messy. So I'm going to skip that. But I want you to see that finding an inverse gives you a method for multiplying matrices. So at least for my students, what I'm going to ask you to do is be able to find a matrix or an inverse of a matrix, and then be able to show me that if you multiply it times its own inverse, you get the identity. So what I'm going to ask you to do is, if I give you a matrix B, you're going to find the inverse of B. And also, I want you to be able to multiply those together to, in fact, get this identity matrix. Okay? And I also want you to know that dividing by a matrix is the same as multiplying by its inverse. All right? And that's the purpose of this. Okay. I think that's going to do it for our video on the motivation behind determinants and inverses. I hope all that made sense. I know it gets kind of deep, and there's a lot of things in there probably that you haven't seen before, and it gets a little theoretical. But I hope you stuck with me, and I hope it made some sense, and I hope it gives you at least some inkling as to why finding these things and doing these calculations might be important if matrices were things that you are working with. Okay. All right. Thanks for sticking with me to the end, and I'll see you guys in another video.